Good morning, everyone. Thank you and welcome for joining the September 2021 session of BrainX Community Live. This session is going to be focused on COVID-19 pandemic and applications of AI. Unfortunately, the pandemic hasn't finished yet, and we are still going through a lot of different phases of the COVID-19 pandemic, and the AI applications continue to grow and show us the way forward. For those who are joining us for the BrainX community for the first time, it is a community of 3,000 plus members, which has had 3+ successful years with the idea of getting together, collaborating for applications of machine learning or AI in healthcare for good. A few of our listed resources, the web page, the very active LinkedIn group, and of course, the monthly session that we hold over here. On our web page, we have 3 sections, the Connect, Data, and the Learn. Connect is the area where we feature our live presentations, and if you miss it, you can watch it on our YouTube channel, where the recordings of our live sessions are available. As I mentioned, we have a very active LinkedIn group, sharing a lot of articles, sharing a lot of information about upcoming meetings, and fostering collaboration. The Learn section, which has a curated list of articles which are annotated and categorized based on different specialties of labeled to you. Of course, these are the links, not the articles themselves, but they take you to the journal or the appropriate site where they have been published. The data section satisfies the needs of many who are looking for open source data sets. These are also now classified based on different specialties. And the links over there take you to these open source data sets that can help you build your next machine learning models. And of course, COVID-19 pandemic has generated a lot of data, and the COVID-19 related data sets are also available through our website. We have been in Europe, and we are planning to bring back the Europe community soon to one of our live sessions. If you want to know which journals are leading in publication of AI-related work, you can go to the journal section and see and follow those journals. And of course, as I mentioned, the community has fostered transcontinental collaboration, especially the COVID-19 pandemic was a perfect platform. This is early in the pandemic where we worked with our featured speaker, Dr. Tavpritesh Sethi from India, to look at determinants of mortality in the US and what we could learn from that. Some early work in the early days of COVID-19 pandemic, which unfortunately still carries on. We have our podcast where you can learn from different experts in the field of AI in healthcare, various researchers, various innovators who talk about their journey, their experiences. And we just recorded Dr. Tavpritesh Sethi, and his podcast should be coming up soon. So look out for that one. It's available on your favorite podcast channels, such as Apple, Google, or Spotify. So please subscribe us and listen to your favorite speakers. And of course, we have been publishing the review of, or the year-end review for the past 3 years for publications related to AI in healthcare. And the 2020 review had a notable addition. We saw so many publications related to COVID-19, which is the theme of today's presentations, that we had to create a separate specialty for it. And unfortunately, the way the pandemic is going, I don't think there is a resolution soon, and we'll continue to see increasing number of publications in this area. So look out for that for the next year too. And with that, I'm going to welcome our speakers who are going to give us talks themed around building AI for COVID-19 pandemic. And our featured speaker is Dr. Tavpritesh Sethi. Dr. Sethi is a physician scientist and associate professor of computational biology at IIIT Delhi, and a fellow of Wellcome Trust, DBT India Alliance at All India Institute of Medical Sciences, also in India. He has been a visiting faculty member at the Stanford University School of Medicine from February 2017 to 2019, and has had multiple publications, 30+ publications, various awards. So welcome, Dr. Sethi. We also have members of his lab, Rintu Kutum, who is a postdoctoral researcher and study coordinator at IIIT Delhi, and Aditya Nagori, who is also a postdoctoral researcher at IIIT Delhi. So thank you for joining us, and we look forward to your presentation. So over to Dr. Tavpritesh Sethi.
We will discuss how we came about addressing some of the COVID-19 challenges and towards building solutions that make use of AI and then transitioning them to real world use cases. So I'll just start presenting. So the way we will do this is I will present some of these overarching themes, not going deep into a lot of details on each one of these because Dr. Rintu and Aditya here will be talking about those, but I will present at a high level what are the kind of themes that we have been addressing in COVID-19 over the past 1 year or so. And then I will invite Dr. Rintu and Aditya with some pointed questions on their journey while they were helping us build these solutions as PhD scholars, team leaders, postdoctoral researchers, and so on. So that will be the structure of this discussion. And I'll start by presenting my screen. So just give me a second here. Okay, so I hope my screen is visible, and I'll be talking about AI for pandemic response. I work at IIIT Delhi and in the Department of Computational Biology. I've also been the founding head for the Center of Excellence at IIIT Delhi, which I'll briefly touch upon what is the aim of doing or aim of the center. So our center essentially is supported by the Delhi government, the Center of Excellence in Healthcare, and our vision is to become a self-sustained technology hub for healthcare by bringing together research, capacity building, industry-grade solutions, and also interfacing with the policy making and implementation partners to really impact the society around us. So our goal is actually not just plain research, but also research that connects with societal needs and problems, not just Delhi or India, but also globally. And of course, we run programs that build capacity, both at master's level and PhD level, and undergraduate level as well. And one of the focus areas that we are building towards is how do we engage more with industry to take some of our healthcare solutions and create solutions as that can be adopted or transferred or actually even lead to startups. So that is the overarching goal of the center. It's not there's a bunch of faculty colleagues who work with us in this center, but in this center we also have a specific wing which is focusing on COVID-19 response, and also we have a specific cluster, Delhi cluster grant, which facilitates that activity, and Dr. Rintu is actually coordinating that activity, and I'll be coming to that. So our mission is to make healthcare accessible and affordable to all through low-cost solutions and innovation, starting with Delhi, and of course, then building up from there for the country and also global communities. So I'll transition to what have we been doing in the pandemic response scenario, not just from the center's perspective, but also from a lab's perspective. And as I said, we'll have some deep dives, insights from the other members of the lab, Rintu and Aditya, but I will start with something which actually started way before COVID, about a year and a half before COVID. We were working in the ICU space, and we realized that a lot of information that needs to be in the hands of people to prevent readmissions in the ICU with outcomes such as sepsis is not available to them in the right format, and of course at the right time. And specifically, we were looking to focus on mothers because neonatal sepsis, as everybody realizes, we work in the pediatric ICU at All India Institute of Medical Sciences. Sepsis is one of the big problems there. And we realized very quickly that to mitigate this challenge, it is not just enough to predict sepsis or associated conditions such as shock in the ICU alone, but we also need to prevent these at the community level. And we realized that in order to do that, we need to get the right information to the right people. In this case, for example, mothers who do not read English and even do not read, for example, newspapers, leave alone the scientific journals or WHO articles and so on. So our goal was, can we use AI to provide summarized, bite-sized pieces of information to people in the community by using abstractive and extractive summarization methods using AI, using text-to-speech, and then delivering these to people through an Android application. And this started way before COVID, but this became really important when COVID struck India. So way back in March of 2020, we repurposed this application, which we call Wash Karo. So Karo in Hindi means do. So do wash your hands. So it basically is around raising water, sanitation, and hygiene awareness among the common people. And when COVID struck India, this was a major theme. So and really there were no trusted sources of information out there when the COVID pandemic struck India. WHO did put out some guidelines. So did the Ministry of Health and Family Welfare. But these guidelines are never read by common people, as was in the case of sepsis. So we repurposed our application. And the way this happens was that we use AI to summarize what WHO guidelines were saying, what news in vernacular were reporting, use extractive summarization methods to summarize these two together, and then generate similarity scores between these pieces of information which are trusted, for example, from the WHO and the Ministry of Health and Family Welfare in India, and the things that were being reported in news. And then using these to filter out the right pieces of information from, and filter out the wrong pieces of information and pick the right pieces of information, and uses summaries in the form of audios, which then were provided to people using text-to-speech and translation APIs. And users, common people, could give feedback on our app and our articles by saying thumbs up or thumbs down. And so this was I think was one of the first, early in March 2020, AI-driven public health interventions, which got a lot of attention. Many people started using it. About 11,000 users actually subscribed, provided information, feedback. It got presented at the WHO Infodemic Symposium, because we were out there to essentially mitigate the infodemic, which is a big problem in all countries across the globe, but especially in India. So, and we showed that we were online with this app for about 3 months before Google pulled the plug on all apps which are non-government apps and disseminating COVID information. So our app was also taken down. But within that 3 months, we gathered enough data to understand what works. So for example, we were able to show that using the relevance counts, people giving thumbs up or thumbs down, we were able to create better filters for people in terms of getting information to them more effectively. And you can see that across time, our relevant counts increased and irrelevant counts decreased. To our surprise, we also found that although more males engaged with the app than females, this is India, so this is not unexpected, but more females engaged with the app in Hindi, which is a local language. Again, pointing that we need informational systems in local languages and building AI, which is more inclusive. for the populations for which it is constructed. This was a very clear pointer towards how do we target, how do we segment our information. And when I say segment, this is not for commercial purposes. This is for social and public health information. So those were some of the early learnings that we actually gained from language models in the public health scenario. But during this last 1 year, one of the strongest themes that has emerged in our lab is the use of unstructured sources of information such as language. And the reason behind that is because, as you would guess, the data are not so easily to come by in COVID, but a lot of unstructured data do exist. And I will leave that to Dr. Rintu Kutum to address that in more detail. So I'll just hint that that's coming up. But what we also did was we started using these language models to different scenarios, not just to language models applied to what was being said in the news or WHO reports, but also language models to social media, even language models applied to sequences of genomes, in this case, the COVID-19 genome. Again, Dr. Rintu will dive into more detail, but I'll give the overview that what we thought was that while strains were emerging across the globe and in India, could we use very similar technologies that we used in, for example, the Washkaro application, which is called word embedding models, to be able to capture the underlying grammar of mutations happening in the COVID genome. Because we know that these gene sequences in viruses or in humans, they have a very clear start point and they are arranged in codons. So can we understand the grammar and then use this grammar to find out patterns in a totally data-driven manner? Once we did that, we were able to show that these sequences actually were able to capture clusters, both in phylogenetic space, which I was showing in the previous slide, and also in the geographical vicinity. And again, Rintu will touch upon this in more detail. More so, we were able to build models that were able to capture relationships that could tell us how these strains were spreading. Because the big question has been, how do we capture strains that may be more infective? So strains, for example, in England and Scotland were behaving more similarly. Strains, Brazil and England were behaving more differently. But could we ask the question that can language models help us predict how the caseloads might change? And we were able to do that. Rintu will go into details of that, but we were able to do that up to 1 month ahead of time, showing that language models and the grammar change in these models does indeed capture some of these emerging variations. That's what I'm showing here, that these underlying grammar changes actually led the increase in new cases. For example, in this case, showed in the United Kingdom. Which means that we could use AI to have a handle on understanding how strains emerge, not just for COVID, but for genomic surveillance of any pathogens of concern. We also used very similar approaches of language modeling on literature to understand how evidence emerged. Because if you remember, early in COVID, hydroxychloroquine, remdesivir, so many papers came out, got retracted, and so on. So we asked this question, can we capture the latent embeddings of the literature that has been vetted, peer-reviewed? And can we understand the latent embeddings of these literature and capture how these themes changed across time? And then what stayed true to the test of time? And doing that via word embeddings, similar approaches, not going into the details, but using word-to-vec models, language models, very similar to what we showed earlier, and then using networks on the top of these models to find how themes emerged. Each streamline here is a cluster in that network, is a community in that network. And a community that stays and gathers weight, gathers momentum, becomes more important, sinks down. And we see that early in August 2020, it was quite clear that COVID is not just a respiratory disease. There are thromboembolic complications, coagulopathies, which were captured in this evidence flow architecture. And since we were able to then capture these links in the networks, we were also able to predict which links may emerge in the future. And that's what our evidence flow dashboard and paper talk about, where basically we showed. And I remember in January, we predicted that psychiatric complication illnesses will see a rise in the coming months. And that's what happened. And we saw that evidence emerge also. More recently in June, our dashboard showed that neurological complications are emerging as a predominant theme. And yeah, so I think that's also well known that psychiatric and neurological complications and sequelae of long COVID are now becoming more apparent. So again, something that we learned from unstructured data. These are not data in the typical sense of the word, because we didn't have neatly organized tabular data sets when we look at these in terms of experimental evidence, but we mined literature, found patterns, and then figured out what stays. Finally, I would comment on one very exciting direction that we worked upon, which uses reinforcement learning. Reinforcement learning is a theme in AI, which is a direction in AI, which actually has been in the news more recently because of the Google Brain's recent algorithm AlphaFold 2 having solved the folding of protein problem in a way which it was unprecedented. So protein folding was a grand challenge in biology. And in November of this 2020, basically, AlphaFold 2 announced that they had achieved in the CASP challenge unprecedented accuracy in being able to do that by using algorithms that make use of reinforcement learning. And this is what the quantum of difference looks between the AlphaFold 2 algorithm and the next best in the CASP challenge, which led protein scientists to comment that now this is no longer a grand challenge, it is a solved problem. We will know how it goes, but essentially it means that now we can design better drugs. Very recently, just about in the last month, Google Brain published their paper on this, and not just that, open sourced their algorithms, which is a huge advancement in the field where people can build upon this. But we were asking this question at the same time in August 2020 with our team, that can we use reinforcement learning to address the problem of effective resource allocation in the context of COVID? And just as computers can learn to fold proteins or play Mario games, this is essentially dependent upon the context that we feed into the model. And some other things such as, so this is a context, for example, number of cases, how many deaths, how many recoveries happen in that particular state of India. Here we're just showing the model for India. What's the population, what's the susceptible population, how many hospital beds available in that state or district, number of ICU beds, ventilators, age distribution, and so on. Remember, this is just a proof of concept experiment that we did. And when we were doing this in August of 2020, we did not have a vaccine in sight. So we were just using projections that if we assume, we did not know how many doses of vaccine will be needed. But if we assume that a single dose of vaccine is given and confers immunity, and there's a lag associated with that immunity, how should we distribute vaccines in a way that we mitigate the spread of the pandemic in the least possible time? That was the basic idea, where we fed in the context We used active predict models and deep queue networks. We had a reward function, and we showed that the network actually learned. How did we know that it learned? Because our simulation models showed that our projections for the future actually show that the spread will slow down. Now, this depends upon which stage of pandemic we are in. If we are in the exponential phase, our models will say we may save or we may prevent an additional 100,000 cases. But if we are in the phase where the pandemic is slowing down, we may save or prevent lesser numbers. But we always showed a positive number of cases prevented by using an intelligence strategy, such as vaccine. We call this platform vaccine. And one of our PhD students from the lab, Raghav Avasti, contributed to this along with team members. And then we showed how we always have a positive number of cases prevented by using such an approach. Now we are actually moving towards building a more general framework where this could be used for general purpose resource allocation problems, where researchers can plug in their reward functions, their context, and ask questions and optimize for results. But that's something that's currently happening. And this is what I was talking about, that we always show a positive number of cases prevented. This dashboard is running and available. The paper is in as advanced stages of review. We hope that it gets accepted, but we are very excited nonetheless about this very first application of reinforcement learning at the public health level towards solving a problem which allowed us to answer these questions and go back to the governments and say that there is a way where we could allocate resources in a better manner. So I think that I'll stop there. I've already taken 20 minutes, actually more. So I'll stop there by acknowledging my team members who actually contributed to all of this, and would switch gears to asking my colleagues who are here, Dr. Rintu Kutum and Dr. Aditya. So Dr. Rintu Kutum is the lead of a project which is supported from the Principal Scientific Advisor's office. It is a cluster project with a cluster of institutions, including our institution and others such as IIT Delhi, AIMS, New Delhi, CSIR, IGI. We have come together to address this challenge of COVID-19, and the PSA to the PM actually supported this project. And Rintu leads this and comes with a very strong background in being able to integrate different heterogeneous sources of data and being able to build insights. So over to you, Rintu. And if you have slides to share, please go ahead. And then I will ask you some questions about your experience in doing so.
Thank you for your kind invitation and also kind remarks. I will start presenting. Is my slide visible?
Yes, Rintu, please go ahead.
Okay, hello everyone. So today I'm here going to talk about my current engagement with Tavpritesh, and my title today is leveraging the diverse data sets for pandemic preparedness and the role of interoperability in this context. So coming to the work which I am going to describe a little bit more about why we actually need to have an interoperability framework in the mind when we are actually designing things which involves team members which are from the diverse background. So in this current manuscript, what we are actually trying to address is that how can we actually leverage out the genome information of SARS-CoV-2 and utilize machine learning and language model to predict the future emerging SARS-CoV-2 variants. So coming to the main context. So basically here in our study, what we have tried to do is actually trying to model the spike gene most specifically, because this spike genes plays a very important role in the interaction with the host cells. So we trying to understand what are the properties of this particular spike genes in a more of a like a data-driven approach, which is typically we use the language model. So in our article, what we actually mainly focuses on actually leveraging the existing dataset, large-scale dataset for SARS-CoV-2 genomes, which was available from the GSAID data. I'll be talking briefly about the highlights that we actually presented in our article. That first of all, we have developed a surveillance model, which was based on the genome information of the SARS-CoV-2, and there we actually treated the words or words as a word as in grammar, the codons of the SARS-CoV-2 genome. And for this, what we have actually used is like around 0.9 million spike gene sequences, and try to model this spike genes characteristics, or in a way the language of the spike gene using the language modeling approach, which where you use the skip-gram algorithm. And along with that, what also we encountered is that once we gain the information of the spike gene of the SARS-CoV-2, we were interested in like how to actually integrate this particular representation of spike gene along with the existing dataset, which is of a different nature. So, for example, what we have actually tried first to investigate whether the utility of this our learned information can be used for predicting the future SARS COVID-19 cases. And for that, what we have done is like we have used some of the algorithms which is widely used in time series analysis, that is the entropy, and use that one to actually proxy to understand what is the information content of the latent dimensions, and use that learned information content to predict the future monthly COVID-19 cases for specific to different countries. And here we have shown for US, Japan, India, and other countries also. Then we use for this machine learning algorithms to model the entropy of the latent dimensions, and we developed our epidemiologically early warning system for the SARS-CoV-2 and COVID-19 case loads. So then we actually try to associate qualitatively, not quantitatively. Right now, our model has a lacuna where we does not have the positional encoding information of the spike genes variations, which was not captured by the skip-gram algorithms. Currently, we are working on positional encoding models, language models like BERT, which are intended to actually capture the positional information of the given sentence, or in our case, will be the codon positions. So in a very short snapshot, first of all, what we do is that we download the GSAID data from the for spike genes of around like 0.9 million genome sequences. Then we leverage the word-to-vec models to understand what is the information content of the latent space that we have learned from the spike genes. Then we have done a two-step process where we have used a quantitative and qualitative analysis of the latent dimensions that was learned from our language model. So in the first place, in the step 3, what we are actually trying to see that what is the information content, which is the entropy of the latent space, and how that is changing across the months. And fourthly, we have done two aspects, which is like a phylogenetic analysis of which already Tavpritesh has mentioned. And also we have done a data-driven unsupervised visualization of our latent dimensions of the 0.9 million genome sequence genome sequences using the TSNE. And further, after that, what we have used is that machine learning algorithm to predict the COVID-19 new cases, and that where we are actually leveraging is the latent dimension space, not the case load, and for the futures. And this can be actually used for the potential surveillance of the COVID-19 variants. So coming to main framework. So basically what our framework involves, the initial framework is that we download the GSAID from the GSAID, the data set, which are genome sequence data, which is a complete high coverage. We exclude anything which is have a low coverage. And most importantly, what we actually have is the collection gate, because we intend to actually model based on the monthly collections per in different countries. Then we have a very high QC and annotation methodology. We are using the COPSEC algorithm. Then extract only the spike genes from those sequences, around 0.9 million strain sequences. Then in the language modeling aspects, what we have done is like we have trained our model from December 2019 to March 2021, and trying to learn the spike genes underneath information content using the word-to-vec model. Then since we have collected the data from April to June, and there some of the data sets were from the past. So the prediction included the data from June 2020 till January 2020 to June 2021. So coming to briefly, so basically what we actually show here is that is the unsupervised latent dimensions that actually we have learned, and in a more of like a 2D visualization. If you see in this first panel, this is the world representation, where we can see there is a clear at the genomic sequence level. In fact, the spike gene diversity has been shown across the time. For example, in China, the diversity has been there, but the genome sequence has been very much less in that case. On the other hand, if you look at the Indian context, we don't have a much of the representation at the beginning from the in the left hand side of the dimension TCNE1 dimensions. So it clearly shows that there is a huge diversity that has been present in the spike gene, and it has a temporal context also into account, which is clearly seen in here, and it has also country specific patterns. So this is during the training period what we have learned the latent dimensions, and when we actually predict for the coming months, from like, for example, here we have just shown for the April to June, where we clearly see that there is a huge diversity changes in that is there in, for example in case of UK. So if you clearly see there, initially it was in the right hand side top corner, there was a lot of points, which is a representation of a SARS-CoV-2 sequence. That is clearly actually now it's coming to the lower part of the plot. So then what we have actually tried to understand, that can we actually capture the information of what is there in the latent dimension in more of like a single metric. So for that, what we have done is like we computed the normalized information content, which is the entropy where you have taken, and we clearly see that there is a dynamic changes that are actually happening across the months for different country, and the information content, for example, in some countries the information content has been reached to the maximum, and later it was actually decreased. And again in the predicted one, we see that there is a huge information content increase for the June month, and likewise you can see for the other countries also, and which represents that this particular representation or the information content has been there, and the diversity of the spike gene protein has been captured appropriately. So then we also try to investigate that how was the pattern from post 2020 December to and before the 2020 for the UK. Clearly we see that the cosine distance from the latent dimension actually clearly highlights that there is a differences which we can see that before the 2020 December and after the 2020 there is a difference is the latent dimensional representation. And for that we also taken as for different countries, it reflects that they have a different representation for that particular durations. Then we try to model the entropy of the latent dimension and see how they are actually differing across different countries. So clearly we said there are some latent dimensional representations can actually have a similarities in the France and Germany, and also then there is a in US and Canada also. So this highlights that there is a pattern that actually can be a common across different countries, and some are typically might be the different in also. then we used machine learning algorithms to actually find it out that what are the entropy latent dimensions where we have here the entropy 32 means that the entropy of the latent dimension 32 clearly show there is some predictability power of that latent dimensions, which will I think Aditya will cover this part aspects in more detail. And this is a snapshot of some of the countries where we actually show that how the latent dimension entropy and also the case are correlated, and how we can able to actually use this particular latent representation for predicting the future cases in case of US and also for Japan. So currently we are trying to and trying to understand the evolution of the SARS-CoV-2 genomes with language model. And also we wanted to predict the emerging SARS-CoV-2 variant using language model if we are able to better understand the evolution. And also to have the integration of diverse large-scale data set, which are open sourcely available for SARS-CoV-2 research data sets, and when integrating that with the language models. Thank you from my side.
Thank you, Rintu. I think very exciting work that you've always been leading. So, Mike, I think Dr. Piyush Mathur also has a question, but I'll ask you a quick question. I think this work is triangulating insights from two very different data sources. One being GISAID, which is a data resource on genomics, the other being Johns Hopkins University's caseload, and then coming to a model which actually is able to predict. So, and I think that is one of these key challenges, that there are so many different heterogeneous sources of information. And so what is your understanding and what is your insight on being able to integrate not just these two, but going forward, diverse sources of information and the role of AI in doing that?
Yes, I think the major challenge that what I actually faced during the project also is that how we were able to leverage, how can we actually leverage the language model outputs to the, in fact, the caseload itself. And there, I think for example, our understanding of since it was a time series data set that we had actually generated, and that actually played a very important role, because that's where we actually decided that we will use something to do with information content algorithms like entropy, which give us the index of also the latent dimensional representation. And coming to the second point, I think most importantly, there are a lot of articles which has been actually published recently also, which actually shows that how heterogeneous and different data sets can actually really enable us to actually predict better the SARS-CoV-2 emergence. For example, like the pollution data set and also the mobility data set. I think the mobility data set has been widely exploited till now, and has been also shown that how the mobility in a country, and also the lockdown and other measures, which actually plays a very important role in actually evolution of the SARS-CoV-2 in itself. And currently in our model, we have not put that context. And I think it will be very much important for us also to actually try to have a framework, or in fact, develop machine learning algorithms, or in fact, language model itself, that how can we actually contextualize those aspects in our model to better predict the future of SARS-CoV-2, actually the SARS-CoV-2 pandemic itself.
Thank you, Rintu. Yeah, I hear that essentially learning representations of different data sets may be helpful in gluing these heterogeneous data sets together along a common dimension, in this case, temporal caseloads and temporal dimension being one. But absolutely. So I think Dr. Piyush Mathur wants to know what kind of, first of all, he actually commends the work, and then he asks what kind of bias is likely to be there based on the variability in genome sequencing itself.
So genome sequence, actually, that's the key part of our, actually one of the very first step that we actually taken into account. It is the sequencing bias that actually can come. And that's where we actually had only very high quality genome sequence data sets. And because if there is a sequence error in a particular nucleotide, that might be, we as a machine learning model learner, we can take as a like a NA, but in a real situation, that error should not be appearing in our model. So that's what we are actually kept in our mind, and we only used very high quality data sets so that any biases that can come from the genomic sequencing level, at least, we don't account that one. And that is the one thing which we definitely had in our mind while we started the exercise.
There might be country level variations in use of these machines, or do you expect those kind of biases?
So to do with, I think since we have modeled the world level SARS-CoV-2, and I think that definitely will not be the case, because as a organism level SARS-CoV-2, we have tried to model using language model. Later we have segregated the latent space according to the our understanding of time scale. But while we were modeling, it was the input data, training data was not contextualized with the time component of it. So right. I will say it is a generic model to start with, but later in the modeling part, like in the machine learning model, which we try to build the case load, there sorry, definitely might be a issue, because the case number and the case load is not directly proportional to the what we had, the sequence numbers we had. But nonetheless, the interesting part of our model was to actually predict the future case load, and despite having less representation of genome sequences from India itself. So that was a one more also plus point that I think I should definitely highlight in our work.
Thank you, Dr. Rintu. So we may come back to you, but in the interest of time, I think we will. I do have questions on reproducibility. Dr. Rintu has been a leading voice in reproducible research. He has been an ambassador for eLife and reproducibility for everyone. He's very passionate. I mean, one of the things that he brings to the lab is everything needs to really be reproducible by any researcher across the globe, whatever we do. I think that's we would love to come back to you and your insights on that, and your thoughts on that. Let me very quickly invite Aditya, who soon he's submitted his PhD thesis, so soon to be doctor. I invite you, Aditya, to present your viewpoint of working with the lab from a different standpoint in the hospital settings and the kind of models we've been working with and challenges and so on. So welcome, Aditya. Please, the stage is all yours.
Thank you, Dr. Tavpritesh, and thank you, Dr. Piyush, for having me here on this nice community of BrainX. So I'll just quickly start presenting my slides in order to present the work that I have been doing. So can you? So I'll just share. So yeah, is my slide visible? So can you see my slides?
Yes.
Yes, Aditya, we can see.
Thank you. So yeah, so I'll just start presenting my work. So I'll be just talking about the insights on developing predictive models. That's what I've been doing in my PhD most of the times, and how can we generalize them. And also the work that we have done for the COVID-19 modeling, where we try to project the COVID-19 cases, and also how we actually use those projections to actually validate the vaccine distribution part that the people in our lab have done. And also I'll be talking about the genomic surveillance, where we performed some machine learning models in order to predict the new cases just based on the sequence information in the language model. So moving ahead, I'll be just talking about the critical events that we try to predict and model and generalize the prediction in different ICUs across USA and India. So the critical events in a disease are the potential stages in a disease which leads to potential irreversible outcomes, and that can also lead to mortality. And if we can provide the early interventions, we can actually prevent these adverse outcomes and mortality. So what actually requires to capture these early or to provide this early intervention is to capture the subtle patterns in the data which start manifesting early enough, which can provide a window of time where the interventions can act. And this requires the application of big data coupled with the application of computational algorithm. But often it has been seen that these algorithms and the big data itself is not sufficient. This might lead to the development of the black box kind of a model. So we also need the feedback from the doctors, and we also need actively the clinicians monitoring and giving feedbacks on these models. So in the nutshell, we have a complex disease condition, and if we can provide the tailored decision models, we can provide the better prediction, and we can give the better care in the ICUs. So this particular idea is quite helpful when we had lots of ICUs being overwhelmed in the times of the pandemic, that we need to prioritize the patient care in order to give the care to the most vulnerable person in the first place. And so what we have done in this work, we try to actually build algorithm around predicting shock, which is one of the most common complications in the ICU, or the conditions in the ICU, where you see there is a circulatory failure in the body and you have a condition of tachycardia plus hypotension. And it's one of the most, as I said, it's one of the most common condition affecting 1/3 of the patient admitted to ICU. So it's very important to create algorithms which can actually predict shock in the ICU. So we actually focused on how can we predict shock in ICU. So we focused on the typical signs of the shock, which is tachycardia and hypotension and the colder peripheries. So the tachycardia plus hypertension can be captured through the physiological time series data. As you can see on the screen, that we have these physiological time series coming from the bedside, and we can actually predict the onset of the disease before some lead time. So this is one of the direction that we can take. And another direction was the thermal imaging, where we can capture the body colder peripheries of the children's, and we can actually predict that who can lead to the shock in the future, or we can actually provide a better monitoring of shock without coming into the contact. So one of the things is that in the pandemic, we were having this notion that the contact-less monitoring has to be happened, because the contact is one of the key thing that through which the infection can spread, and we can avoid that by building the non-invasive and non-contact methods or introducing these modalities in the ICU. So I'll be just talking about how we actually created models around the time series based data. So first, what we have done here is we generated the cohorts, where you can see there these are the patient time series. These are the different patients, as you can see, and the time series of these patients have been visualized here. So what you can see, this red region is the region where you have the disease, and the blue region where you don't have the disease. And we can make use of this blue region where you can observe the data and predict what's going to happen in the future. So here, particularly in this work, we use the shock index to label the time series on a minute-to-minute basis, and we use the different criteria to do so. So here's the full pipeline of our model, where we extracted the cases and controls from the data, from the time series data, and we extracted, so we kind of extracted features out of the observational part of this time series in order to predict the future event. We use different sort of models, as you can see. So for the model development part, we use the hand injury time series feature, then multivariate time series itself. So in the hand injury time series feature part, we use the classical machine learning model, which can use the features in order to give the prediction. And we also use the deep learning based models such as CNN LSTM and bidirectional LSTM in order to model the multivariate time series. So this model development part was carried out on a 200 plus ICUs, publicly available 200 plus ICU EICU database, where we have we can actually train models on different ICUs. So in order to generalize this model, what we actually applied a technique where what we have done is that we built models on a few ICUs and generalize or try to learn the or validate the models on the completely new ICUs and test them on the completely a new set of ICUs, so that the model and the parameters learned by the algorithms can learn the intricacies of the data on the new data or the new hospital's data. So that's why we divided our data into hospital-wise 5-fold splits and trained our model on the EICU data, which is a completely heterogeneous population of data. Then we moved ahead and tried to generalize these models on the external validation settings of the MIMIC and Safe ICU. MIMIC is the MIT-based setting, and Safe ICU is our in-house New Delhi-based setting where we try to generalize these models. Also, our Safe ICU setting is the pediatric setting where we try to see the potential of our model to generalize on the completely new age group, which was not present in the EICU data. So we got a very good accuracy, such as like 86% of AUC in the EICU data itself. And then we also got the 93% of AUPRC in the EICU data set. And our model performed quite consistently across different lead times, which is 0 to 8 hours. And across different age groups, also our models perform very well. And when see around the different ICU types, we saw that consistent performance across different ICU types, stating again, emphasizing that our models are able to generalize across different age groups, ICU types, and lead time. We also observed that our model performance start to increase as the patient stays increase. So for the longer stay in the ICU, our models were performing very well. So as you can see, the recall of our model has increased after 13th hour, close to 90% or above 90%. So these are the some observations we observed in our models, which performed very well on the EICU data itself. Then we try to generalize our models, and before generalizing, we try to see the interpretability of our model itself. So we saw that so these are the basically shape algorithm where we try to use the game theoretic based methods to see the influence of each feature on the model performance. And as you can see, the larger the influence, so the higher the value of these shape values, higher the influence. So we observed that heart rate minimum and arterial systolic blood pressure minimum are the two key features which had the highest influence. Then we have the respiratory rate, aggregate linear trend, respiratory rate, Benford correlation. These are different time series features that we extracted and found having the influence on the prediction. Then we actually evaluated a different generalization scheme. So we first of all plotted the standalone model in order to compare it with a different generalization scheme, which is the retrained or fine tuning on the new data, and then without retraining. So with the retraining and fine tuning, we saw the increase in the performance. As you can see here in the MIMIC data itself, you can see that retrained model had the use of AUPRC of 93%, and without retraining it was 89%. So we saw a slight improvement with the retraining, but without retraining also our models were performing good on the MIMIC data. But without retraining, we couldn't found a good performance on the Safe ICU data, particularly because of the pediatric age group. We need to fine tune our model on the new age group. So we fine tuned our model on the pediatric age group, and we saw equal performance on the MIMIC, equal performance on the pediatric data as that of the adult population. So this is so we actually tried to implement our models in a Docker-based application where anybody can actually use these models and readily download from the GitHub, and so this is the application, the demo of the application where we have built this ShockUpred tool, where the user can upload the data and can make predictions in their ICU itself. So as you can see, we can upload the data, and this upon applying the predict function, our algorithm can give the prediction probabilities, which can be used for in any ICU using this open source tool. Then we actually use the thermal imaging based pipeline in order to predict shock. So using this pipeline, what we can do is that we can identify the colder peripheral region and use it in the model equation to predict shock. And this was done first in the first step. We did it manually in order to establish a proof of concept.
We are a little bit above time, so if we can quickly wrap this.
Yes.
We do have some questions, so yeah.
Of course. So I'll just take 2-3 minutes more and I'll just finish. So we use the computer vision based pipeline in order to automatically extract these features, these gradients, to predict shock. And this particular algorithm can be used as a non-contact modality in the community, where in the current time itself, we were seeing that there is a shock syndrome spreading across India due to dengue fever and so on. So this algorithm can be used by the ASHA workers in the community to detect shock. And so in the pandemic modeling, we use the epidemiological models such as ACIR models then to actually predict the new cases. And we also use the agent-based modeling, where we use the classical epidemiological model-based setup to be modeled using agent-based modeling. And we did the projections of the COVID-19 in India. And we use these projections in the reinforcement learning algorithm developed by our colleague Raghavasti and team to actually distribute the vaccine across different states of India. And we see that how our algorithm was able to, distribute vaccine in an effective manner, so that we can decrease the new cases in a significant manner. So this is what we can see through this plot, where the red line is the new cases when we apply the reinforcement learning based vaccine distribution strategy. In this modeling part itself, we as Dr. Rintu and Dr. Tavpritesh talked about the genomic surveillance part. What we have done here is that we try to model the new cases with the blip dimension extracted from the language models. So this blip dimension actually represents the genomic sequences. So what we observed here is that using our cross correlation analysis, that the blip dimension were leading in the countries such as Brazil, where you can see higher correlation on the X side, which on the negative side, which means the blip dimension start showing some predictive ability prior to the happening of the new cases. So we try to model this. So we observed it in exploratory analysis, and then we modeled it in machine learning algorithms such as Baruta, where we can see that there are some important blip dimensions which can be used for the prediction of the new cases.
Sorry to interrupt. I think we do need to take some questions. No, thank you so much for summarizing and discussing these directions. I think temporal models have been your forte, whether it be temporal models in the ICU settings or temporal models that you applied in strain settings, again, pointing out the value of collaboration. So I think I'll just jump to questions, Aditya, for you. So any work relevant, so Priyam Prakash is asking, any work relevant to predicting COVID positive who had after symptoms and revisited or readmitted? I think so. This is a question that I can take. No, we have not done this. We do not have access to this data, but in the Delhi cluster project, we are trying to have these data available to us. But the short answer to this is, this has not been a direction that our lab has so far worked in. Piyush is asking if some early features of shock are different amongst COVID patients versus other septic patients. and late stage, probably they're going to be the same. So Aditya, although I would just say that we have not modeled COVID patients separately in this, but Aditya, do you have any thoughts on this?
So as far as I read about the septic patients, there was this article which actually says that the COVID-19 is basically sepsis. The deaths happening in the ICUs are because of the multiple organ dysfunction, which was common in sepsis and septic shock patient and the COVID-19 patient. So, so it is essentially, I mean, I can share the article after the talk that it talks about that. So basically, sepsis modeling or septic shock modeling is essential because it helps, prioritizing the COVID-19 patient in the overwhelmed ICUs across the globe. So yeah.
Certainly, but yes, so adding to that, I do think that there might be different physiological features in early stages of COVID versus because of it being such a systemic disease, we might see some early, although there are other conditions also where cytokine storm happens. And so, but the short answer is we have not studied that. And perhaps we did not have those many patients of COVID in the pediatric ICU. But we do think that it's a question that is definitely worth asking going forward.
Yes.
I think very quickly, a very important question that I would like you to address. Sherry Gavidon is saying congratulations and thank you for the amazing research. How might we communicate to clinicians and decision makers? For example, the models that we talked about, reinforcement learning or the septic shock model. So what is your experience with that?
So yeah, I think we can have a clinician on board from the very beginning of the model development itself, because during the development phase itself, there are a few things that might miss out, which clinicians might point out. And when we have the models in place, as discussed with the clinician, we can take right feedback from the clinician, whether if the model is giving right predictions or not, and if the interpretability of the model is working rightly or not. So if a model has given some prediction that this patient might lead to the outcome of the disease, and our interpretability based features coming out of the models are telling something else, then it might not make sense to the clinician. So it is important that clinicians are monitoring and also understanding what explainability has been given by the model and whether it is working.
Thanks, Aditya. I think you highlight two very important points about clinicians being partners from the very early stages and having models that are more interpretable and explainable. There might be many more ways in which I think ultimately it will have to come to a process level and a human level interoperability. But we do believe that we are still far away from that in achieving that in healthcare with AI. But our lab is focusing on some of those directions with frameworks. Rintu is working towards that, and I think that will be key. How do we build trust in the models by taking all these steps? Sorry, Piyush, for being over time. I'll hand over the mic back to you. And,
no, thank you. Thank you, Tav, and thank you, Rintu and Anita. I think that was some awesome work that you presented over here. And of course, some great questions and follow-up. We could do this for hours together probably, but for the sake of time, we'll end there. And I would encourage our viewers to go and to Tav Labs website and read more about their work over there, and some of that is coming up in upcoming publications. So thank you all for joining us. We are going to end this session over here and see you next time.
Sure.
Thanks, everyone. Thank you.